propositions are being applied in logic gates, logic circuits, and how we can simplify the circuits using the different operations which we can perform on propositions. Fine. So today we are covering Boolean algebra and circuits. So let us see few terms and then we will move forward on applying these for our real life circuits. So we will study Boolean algebra for implementing these. Under Boolean algebra, we are going to cover few laws like associative law, commutative, distributive, identity, complementation laws, idempotent laws, absorption laws, involution law, De Morgan's laws, okay, and duality. Then thereafter we will cover logic circuits. Fine. After logic circuit, we will simplify Boolean algebra based expressions. We will create Boolean expressions and vice versa. From the circuit diagram, we will try to create expressions. Fine. And after that, we will start the dynamic programming. Fine. This is all that we are going to cover today. So now let us start. Fine. In previous session, we had studied about proposition. Now let us start with the tautology. What is tautology? What is tautology? Any proposition whose value is always true is your tautology. So while creating any table, suppose we are having P is a proposition. Under P, if always we will get value as true, then we can say that P is tautology. In the similar fashion, if for any proposition we always get value as false, then we can say that this proposition is contradiction. So we have here we are defining two type of proposition. One is tautology. Tautology is where every value will come true. So in truth table, we will have values as T under tautology. So we can define tautology as any proposition for which our value is always true. For example, a round circle. Circle is always round. A round circle. So we will have value true. How we are going to define contradiction? Contradiction is any proposition for which value is always false. For which value is always false. See here in the table, I am filling false values. So any proposition for which I am having false values is our contradiction. Fine. For example, John is alive. For example, John is alive and dead. This is what contradiction. So value of this proposition will always be false. So under this, we will write F. We will write F always. So this is what contradiction. Fine. How we are representing propositions? We have set of proposition. Set. Like we can say set of colors. So C is set of colors. Colors may be blue, green, red. So this is the way we represent set. In the similar way, we can represent set of proposition. So using capital S, we can represent set of propositions. Fine. So here S is set of propositions. So what are the operations that we can perform on set? We have conjunction and disjunction. Like P and Q. This is conjunction. And P or Q, this is disjunction. So these are the operations that we can perform on proposition. Fine. Now let us see few examples. How we write? We write for all. This symbol states for all. For all. This is the symbol for all. For all P and Q belonging to set of proposition. For all P and Q belonging to, this symbol is for belonging to set of proposition. We can write what we can write? Conjunction P comma Q. That is P and Q. Similarly, we can write or a disjunction P comma Q as P disjunction Q. And for negation, we can write P. P's negation is this tilde symbol is used. Tilde symbol is for negation. For example, if P is true, okay, then negation of P will be false. Fine. In this way, we can represent negation. Is it clear? My screen is visible. Am I audible?
Yes,
Yes,
ma'am.
yes, yes.
Fine, fine. So we have other laws also. One of the law is identity law, where we get the proposition back as result. How? P or F. F means false value. F means false value. So let us make a table. P and F. Let us see. Here P or F. Fine. P or F. Suppose P is 0, P is 1. False. False states 0. Fine. So P 0. When P is 0, result is 0. When P is 1, result is 1. So this is 0, 1. Again, we are getting 0, 1. Same. It means result is same. This was input. This is output. So result is same. Same. It means identity law states that if you do ORing means this. If you do ORing, yani ki disjunction of proposition with false, we will get same proposition as result. So if we take value of P as 0, we will get output as 0. If we will take value of P as 1, we will get output 1. Fine. Is it clear? Similarly, identity law also states that if we apply conjunction, yani ki and conjunction, it means and P and T. T means true value. True value means 1. So P, T. P 0 and 1. T means 1. So what result we will get? We will get P. Fine. And here what we are performing? We are performing what? Yes. And so 0 and 1 will give you result as 0. 0 and 1 will give you result as 0. And 1 and 1 will give result as 1. So see, input, when input is 0, output is 0. When input is 1, output is 1. So here answer is P. So in identity law, when a proposition is disjunction, fine, then with the false value result is P. When conjunction is done of proposition with true value, result is again P. That is why this law is known as identity law. Now we will see how Boolean algebra is being done. In Boolean algebra, we look for all set of propositions, all different operations that we perform, false and true values. So in Boolean algebra, what are the things that we take into consideration are set S, all the set of propositions, all the different operations that we can perform, and true and false value. Let us see few examples. We are having few examples. Let us consider associative law and see. Here we can see these are X, Y, and Z. These are 3 variables. What are different operations? Operations are disjunction. Operations are disjunction. Disjunction means this, yeah, or. We can see operations as conjunction. junction, yani ki we can have and operation. Fine. So here, as what associative law states, we can write x or y or z, and we can write it as x or y or z. These are equivalent. Similarly, we can write x and y and z, and this is equivalent to x and y and z. These are equivalent. So result on left hand side is equal to result on right hand side. So we can write in this way. These are what associative laws. Commutative laws: x x disjunction y is equal to y disjunction x. Similarly, x conjunction y is equal to y conjunction x. Fine. This is what? This is disjunction. And this is what? This is conjunction. Fine. These are commutative law. Okay. Fine. Then distributive law. X. Here y and z. So we can write combination. Combination like this. So x or y. In between we will get this, and then x with z. So we can write x or y and z is equal to, fine, combination of this x or y, combination of this, fine, x or z, and in between this operator. So this is distributive law. Fine. Identity law. This is x is what? X is proposition. X is proposition. F is false value. When ORing is done, this operation is called or disjunction. So when ORing or disjunction is done with proposition with a false value, result is always the proposition. For example, if here we will take x as 0, the result will be 0. If we take x as 1, result will be 1. In the similar way, if a proposition is ended with ended yani ki conjunction, fine, conjunction, it is done with a true value. True value means 1. So result is always the proposition. Fine. If it is 0, result will be 0. If it is x is 1, result will be 1. Fine. Then we have complementation laws. Here we are dealing with the complement. It is also represented as like p. Complement of p is not p, or this, or this. In this way, complements are written. Fine. P's complement. This or this or this. P's complement yani ki negation of p, or tilde sign p, or p dash. Fine. So here let us come back. X and or we can say conjunction. So x and x bar. X bar means complement of x. Complement of x. X and complement of x will give false value. See, x and complement of x is giving false value. Fine. False value means 0. See here, x. Suppose x is 1 and complement of 1 is 0. So we will get value as 0. In the similar fashion, if x is 0, complement of x will be 1. So ending of 0 and 1 will give value 0. Fine. Is it clear? In the similar way, complementary law, x or x bar is equal to true. X is 0 or x bar is 1. True means 1. Yes. If we will take x as 1 or 0, so 1 or 0 again it will give 1. Fine. In this way, complementation laws work. Then we have ident idempotent laws. It means any proposition when it's oring or disjunction or disjunction is done with itself, result is same proposition. For example, x, see x, fine, and result will be x. See, if it is 0 and oring is done, result will be 0. If both are 1, oring will be done, result will be 1. Fine. Is it clear? This is what idempotent laws. You have to remember these laws. Then we have absorption law. X, okay, X disjunction, fine. And inside bracket you have opposite sign. Here you are having disjunction, so inside bracket you are having conjunction. Make it very clear. Here you are having disjunction and inside bracket you are having conjunction. So X disjunction inside the bracket conjunction is equal to X. Anything you can prove using truth table. Anything you can prove using the truth table. Simply write values X, Y and find X disjunction, X conjunction, Y. Automatically you will get the values and you will be able to prove. Fine. Then involution law. Involution law means P's complement, again complement will give you P back. Fine. Is it clear? For example, 0, 0 ka complement, again complement will give us 0. See, 0 ka complement is 1. Fine. And 1 ka complement is 0. So right hand side was 0, left hand side is 0. Fine. Is it clear, class? P. P का complement. Fine. P is 0. तो 0 का complement. 0 का complement 1 का complement. 1 का complement 0. Answer is 0. Fine. Involution law. Then De Morgan's law. It is very important. It is very important. See here. This is first and this one is second. Why? Here you are having disjunction. Fine. And it is also known as OR. So we can say X or Y bar. X or Y bar is equal to X ka bar and Y bar. Fine. In the similar way, here you are having what? Conjunction. Here you are having conjunction in B. Fine. So X conjunction is also known as and. So X and Y ka bar, Y ka complement is equal to X complement or Y complement. This is or disjunction. So these are De Morgan's law. Fine. Then dual. How you can find the dual? How you can find the dual? In dual, suppose this is the expression and you have to find the dual. You have to reverse the sign. Where you are finding or, you have to make it and. Where you are finding and, you have to make it or. So the disjunction will be, sorry, so the dual of P will be, this is P. Dual of P will be X and X or Y. This will be the dual. You have to reverse the sign. Where you are having or, you have to make it and. Where you are having and, you have to make it or. This will be your dual of proposition. Fine. And where we implement these? We implement all these things in our logic circuits. Is there any new student who has come and I have not admitted? Yes. Is there any student? Is there any student waiting? Yes, is there any student waiting for the class? Should I need to admit anyone?
We do
Actually,
know,
no,
ma'am.
ma'am.
Okay, so all are present. My screen is visible?
Yes.
Yes, ma'am.
Okay.
Yes,
Where we
ma'am.
implement all these things? We are going to implement all these things in the logical circuit. Actually, for any device, this is the logic circuit box. We simply provide inputs, and what we get? We get output. This is the simplest diagram of a logic circuit. Let us see. Let us see. In computers, we are having three types of basic gates: and, or, and not. Do you know how to draw these gates? This is what? Which gate? Anyone?
This is AND
And
gate.
get.
And gate. Fine. And gate means conjunction. Suppose this is A and B. So output is A and B. Fine. Anyone? What type of gate this is? Suppose we have inputs P and Q. Okay. Fine. Output will be P or Q. So this is OR gate. This is AND gate. Right? This is OR gate. Now coming on to NOT gate. This is NOT gate. Suppose this is P. So here output will be negation of P. Yeah, P complement. Is it clear? Is it clear?
Yes, ma'am.
Now we have two states, on or off. On is 1, off is 0. Right? So here in any circuit, we can have value 0, 0 input. What will be the output? This is AND gate. This is AND gate. What will be the output? 0, 0. Output will be 0. Output will be 0. Fine. If we are providing 1 and 0, so output will be, yes. In case of 0, 0, output was 0. We are
Zero.
providing input 1 and 0.
Zero.
1 and 0. Output will be
Zero.
0. Suppose we are providing 0 and 1. 0 and 1. 0 and 1. Output will be 0. But if we will provide both the inputs as 1 and 1, so 1 and 1, output will be 1. Fine. This we have represented in form of this table. X1 is one input, X2 is another input. And this is AND gate. And we can represent output as X1 and X2. So this is X1 and X2. For both inputs at 0, output is 0. For 0, 1, output is 0. For 1, 0, output is 0. Only for both inputs as 1, we have output as 1. Is it clear? AND gate. So the
Yes, ma'am.
conjunction is also known as AND. Fine. And it is represented with the help of AND gate like this. So here we are having two input lines, two input, two input lines. Fine. And one output. And one output. Fine. OR gate. OR gate. Fine. OR gate. These are what? Inputs. Inputs are X1 and X2. And how we can represent output of OR gate? X1 or X2. Fine. This is what? OR. So the input may be 0, 0, input may be 0, 1, input may be 1, 0, input can be 1, 1. And this we have represented in form of this table. This is input 1, this is input 2, and X1 or X2, this is the output. Fine. So when both are 0, output is 0. 0, 1, output is 1. For 1, 0, output is 1. For 1, 1, output is 1. It means for when any input is 1, any one of the input is 1, we get output as 1. This is the OR gate. Then NOT gate. NOT is represented, suppose X, we have to represent it NOT, then NOT X or NOT X. or x complement. These are the ways in which we represent. Fine. So if here input we are having 0, so output will be 1. If input will be 1, output will be 0. And how this is represented? In form of truth table. X and x bar. When x is 0, x bar is 1. When x is 1, x bar is 0. Fine. Is it clear? Okay, fine. And these tables,
Yes,
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 ma'am.
ma'am.
these tables are known as truth tables or logic tables. X and Y. These tables are known as logic tables or truth tables. So we have seen for and, or, and not. Fine. Find the Boolean expression for the logic circuit. So this is the logic circuit. Fine. See here. 1. See in diagram 1. X1 and X2 are inputs. Which type of gate is this? 1. Which gate is this?
Or get, or
Or
get.
Or.
or
Or
gate.
Right. That is why we have written output as x1 or x2, because the inputs were x1 and x2. So the output is x1 or x2. So come to gate number 2. Which type of gate it is?
It's and get.
And
and
gate.
AND gate. And the inputs are x3 and x4. So output we have written as x3 and x4. Fine. So gate number 3. See, this is a NOT gate.
No,
NOT gate.
not get.
So
Yes.
here we have make complement. Output is complement of input. So input is x3 and x4. So now the output coming out of this NOT gate is x3 and x4 ka complement. Suppose here we are providing value 0. So here we will get 1. Fine. Now see the gate number 4. Gate number 4. Which type of gate it is?
And gate.
And
And
get.
gate.
and
It's and get.
And gate. And see, this is input 1 and this is input 2 for this gate. So the result is, see here, result is input 1 and input 2. Fine, is it clear? So input 1 is x1 or x2. X1 or x2. Input 2 is x3 and x4. X3 and x4. And what we are performing? We are performing AND operation between them. So this is the output. Is it clear? Class, is it clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes.
See, next question. See here. This is one number gate. 1. Input 1, that is x1. Input 2, that is x2. And which type of gate is this?
Or gate.
or
Yes.
gate.
OR gate. Fine. So what is the output? X1 or x2. Is it clear? Fine. Is it clear?
Yes, ma'am.
Yes,
Then we
ma'am.
are coming
Yes.
to gate second. In gate second, negation is done. So here we are having output as negation. This complement is negation. Whatever inputs we have passed, now these are being negated. X1 or x2 ka whole bar, yani ki negation. Then x3. This, which type of gate is this? And. Fine. So this and x3. So what is the output? And x3. So this is the output. C is equal to this. So we can write C, yani ki output is equal to this. And what operation we have performed? We have performed AND. Is it clear? Because third number gate is AND. Is it clear? Class, is it clear?
Yes, ma'am.
Okay. So suppose we have x1, x2. Fine. Suppose we are performing and we are getting output. So x1, x2. We are performing and. So what will be the output? How we will represent the output here? X1 and x2. Suppose, yes, suppose we are taking this output as input for another AND gate, gate number 2. So this output of gate 1 will act as input of gate 2. And suppose we are taking another variable x3, so we can write this. So can anyone tell what is the output here? Last output. Last output will be x1
X1
and
X2
X1
x2.
and
Yes,
X2
and
And X3.
and
x3.
X3.
Fine. So output will be x1 and x2 and x3. Fine. Is it clear? This is going to be output. Fine. Okay, let us take another example. Let us take another example. Suppose we want x1 complement and x2 or x3 and x4. Can you draw this? Try to draw this.
Yes, ma'am.
Yes, yes, try to draw this. Please draw x1, x1, and we need complement of x1. So x1 complement means it means negation. Negation. Fine. Complement means negation. So x1 ka complement. This is what x1 ka complement. We need x2. We need x2. Fine. We need x2. So x2. And what we have to do? And. Fine. So we have to do and. So here what we get? We get x1 bar, any negation of x1 and x2. Fine. Now we have to perform ORing. ORing. We need OR gate. Fine. So we need this output will be input for another OR gate. So this is the OR gate. Fine. And what is the another input for this OR gate? This is x3 and x4. So x3 and x4. We need one AND gate. This. And this is the output x3 and x4. Fine. Is it clear, class?
Yes, ma'am.
Now we have final output this x1 and x2. Fine. And or x3 and x4. Is it clear? Class, is it clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, fine. Fine. And now I am giving you two questions. See here. Have you seen? Is the screen visible?
Yes, ma'am.
Okay. Just try first part. How can you represent it in the form of Boolean expression? Boolean expression.
First one is X1 and X2 negation or bar.
Fine. This is first gate. This is second gate. Fine. So we have two inputs, x1 and x2. And this is what? This is OR gate. OR gate. Okay. So output will be x1 or x2. This is will output. And now here we are having negation. Negation. So yes, x1 or x2 complement. Fine. Is it clear? Class, is it clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Now let us try the second one. Fine. Let us try the second one. So let's see the first gate. X1, X2. And this gate is AND. So the output will be X1 and X2. Now see the second gate. It is negation. It is negation. So the output will be X1 and X2 negation.
All negation.
Fine. Okay. See the third gate. Third gate x3. So here output will get s3 ka
X
x3 ka
negation.
negation. ठीक है? You can also write like x negation of x3. You can also write like x3. Somewhere in books you can find x3 bar. There are several ways, or x3 dash. You can write in any one of the way. No problem. So we have inputs. We have inputs at, yes, this is and this. We in fourth gate. Come to the fourth gate. Fine. So in fourth gate, you have and. So inputs are this and this. I have ticked inputs. So we can write x1 and x2 ka bar and AND gate and x3 ka complement. Fine. Is it clear? Is it clear?
Yes.
Class.
Yes, ma'am.
Yes, ma'am.
Yes,
Yes,
ma'am.
Okay. Now the question is, how can you construct a logic circuit? Vapas, converse. How can you construct a logic circuit out of a Boolean expression? Fine. Now you have Boolean expression. Boolean expression is given. Boolean expression is given. And you have to construct. Okay? Construct circuit diagram. And you have to construct circuit diagram. Fine. Is it clear? So how will you proceed? Let us see what operations are there. You have negation. So how negation is represented? Like this. This is for negation. You can see and. So how and is represented? This. Second.
Mhm.
You can see or. So how or is represented? See the third diagram, how or is represented. So you should know how to represent like this. Only then you will be able to construct the circuit diagram. So you will be given Boolean expression and you will be asked to create the circuit diagram. Fine. Okay. Yes. Please try. This is Boolean expression and you have to create the circuit. Try to create the circuit. Just try. Class, just try. So step by step, I am showing here. Step by step. X bar ka negation. X bar, negation of X bar. So X, negation. And this is X bar. Fine. Is it clear? Then what you have to do? Step 2. Step 2 is ANDing with X2. Now you need another input, X2. Another input. This is X bar. Now you need another input, X2. And what operation you have to perform? AND. So we need AND gate. And what we will get? We will get this. We will get this as output. ठीक है? X1 का bar and X2. Is it clear?
Yes, ma'am.
Now further, next step. Now we have these things. Now we have to find this, and after that, A or B. But we have to do this like. Next. See here. X1 or X3. Fine. X1 and X3 or. Fine. Or. यानी कि X1 or X3. Is it clear? Now we have this as A. And we have this portion as B. Now we have A and B ready. And what we have to do? OR. So what we have to do? OR. And we will get the output. Let's see the next step. This is the next step. This is the next step. Fine. See, this is A. This is A. This is B. And what you have to perform? OR. So one input, I am showing with the red line. One input and second input, and finally this is the expression. So this is the actual diagram. Fine. Is it clear, class? Is it clear?
Yes, ma'am.
For above
Yes, ma'am, it's clear.
yes, this is the actual diagram, circuit diagram. Circuit diagram. Now what you can do, from expression, from Boolean expression, you can create circuit diagram. Fine. Second, from circuit, you can create expression. Fine. You can, conversely, you can create expression. Given expression, you can create circuit. If given circuit, you can create the Boolean expression. Is it clear?
Yes, ma'am.
Yes,
Oh,
ma'am.
now create logic circuit for this one. Try to create.
Okay.
Yes, create logic circuit and make truth table. Create logic circuit and make truth table also. X1. Fine. Or. Now ORing will be done with this. For this we need X2 ka bar. So X2 not gate, and here we are having X2 ka bar and X3 and X3. So X3, fine. This is what? This is X2 ka bar and X3. Is it clear, class? Is it clear? And this
Yes.
has to
Yes.
be done ORing with X1. So these are two inputs, and finally you will get the output, this output. Is it clear? So the logic circuit, we have created logic circuit. Now we have to create logic table, truth table. Truth table. How many variables are there? How many variables are there?
Three,
Three
three
variables.
variables. Three
Four.
variables.
X1, X2, and
Three.
X3. And you have to find X1 or X2 bar and X3. Are you able to do this?
Please go
Three
ahead,
variables.
ma'am.
Yes, three variables. Na? 2 की power 3, 8 rows. Fine. 8 rows. So 0, 1, 0, 1, 0, 1, 0, 1. Fine. Then 0, 0, 1, 1, 0, 0, 1, 1. Then 4, 0 and 4, 1. Is it clear? Now you also need, before coming on to this, you need to find X2 bar and X3. So you also need what? X2 bar and X3. Fine. So suppose we want to find X2 bar. X2 bar will be 0 is 1, 0 is 1, 1 ka 0, 0, opposite. Fine. X2 bar. And X3, X2 bar and X3. This is X2 bar and X3. So 1 and 0, 1 and 0, 0, 1 and 1, 1. Fine. And in this way, now you need what? X1 or X2 ka bar and X3. Now you can finally calculate. Is it clear? Step by step you can perform. Is it clear, class?
Yes, ma'am.
Yes, ma'am.
Okay. See, construct logic circuit represented by Boolean expression this. Are you able to view the Boolean expression, class?
Yes,
Are you
ma'am.
able to view? Fine. You can view the Boolean expression. This is what? X1 ka bar. So how can you do X1 ka bar? X1 negation. Negation. We will get X1 ka bar. And X2. And X2. So X2, and we will perform AND. Fine. So here we will get X1 ka bar and X2. Is it clear? Is it clear? Now we have
Yes,
to
ma'am.
perform
Yes, ma'am.
OR. We have to perform or. This is the gate for or. Okay. For oring we need input x1 or x3. So x1, x1 here, x1, then x3, x1, x3. We have to perform or. This is x1 or x3. Fine. So at one side we have x1 or x3, and second side we have this, and this is the final output, that x1 ka bar and x2 or gate, or this x1 or x3. Is it, class, is it clear?
Yes, ma'am.
Class?
Yes,
this,
ma'am.
this is the circuit that I have drawn here. Fine. How we can draw? Now is it clear? Done. And here in the left hand side I have shown step by step how you can create it stepwise. Fine. Now this is the expression. Just create the circuit. Class, create the circuit. Yes. Create the circuit. Can you create it?
Yes, ma'am.
x1
We will try.
bar or x2 and x3 ka bar. Fine. And this is suppose A. This and. Fine. And this whole expression x2 or x4 ka bar. This is your B. Fine. Fine, class. Okay. Now what you need? x1 ka bar. So x1 is one of the input. You need x1 ka bar. Or. So you need OR gate. Or. Now you need x2 and x3 ka bar. So you need x2 and x3 ka bar. x3 ka bar. x2 and x3 ka bar. Which type of gate? And. Is it clear? So this is what x2 and x3 ka bar, and here you are having x1 ka bar. So this pura complete A is coming as output. As output you are having x1 ka bar or x2 and x3 ka bar. Is it clear? Is it clear? Class, is it
Yes,
clear?
ma'am. Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am. It's
In B
clear.
part you are having x2 or
Yes, ma'am. It's
4 ka
clear.
bar. So x2, so you can take x2 from here, x2 and x4 ka bar. For x4 ka bar, x4, this is your x4. Fine. X4, and you have to do x4 ka bar. This is x4 ka bar. Fine. And what type of operation? Or. You have to perform or. Is it clear? And here it will come. And what is the final operation? Final operation is and. So you have to perform and. Is it clear? Is it clear? Fine.
Yes, ma'am.
This is x2 or
Yes,
x4
ma'am.
bar. Fine. Is it clear, class? So in this way you can practice.
Yes, ma'am. It's clear.
So can you make this? Find the logic circuit corresponding to expression x1 ka complement and x2 or x3 ka complement. Can you construct circuit diagram for this?
Yes, ma'am.
ma'am.
Yeah.
Right?
Yes, ma'am.
Try x1 ka complement. So this is x1 ka complement. Now you need and. So you need and. Fine. For and you need this x2. So this is x2, or you need or x3 ka complement. So x3 x3 का complement. Fine. Now ending. Fine. So this is x1 का complement and fine x2 और x3 का bar. x2 और x3 का bar. Is it clear? Is it clear, class?
Yes, ma'am.
Okay. For question number second, you have to construct logic table as well as logic circuit, both the things, logic circuit as well as logic table. Can you complete the logic table given below? Can you complete it? Can you complete it?
Yes, ma'am. Yes, ma'am.
Yes,
Is
ma'am.
it easy? Yes, yes. It is easy. Right? All possible combinations. You need all possible combinations. So x1, x2, x3, simply 01, 01, 01, 01, 00, 11, 00, 11 in 40 and 41. These are all rows. Now x1 or x2. x1 or x2. So x1 is 0 or x2 is 0. So here result will be 0. Fine. Is it clear? Is it clear?
Yes, ma'am.
Now x2, it can be x2 or x3. Fine. Is it clear? And what is this? x1 or x2 and x3. So x1 or x2 you are having here, or ending करनी है with x3. Whatever will be the result, that will be here. So you can complete the table also. Fine. Then you have Boolean function. You can represent the function as function 0, 0. That is 0. It can be 0 का complement and 0 का complement. So 0 का complement is 1. 0 का complement is 1. 1 and 1 is 1. Fine. Your function can be 0, 1. So 0 का complement and 1 का complement. So 0 का complement is 1. 1 का complement is 0. 1 and 0 is equal to 0. So you can have different types of functions. See the 1, 0. 1, 0. It means first will be 1 and second will be 0. So 1 का complement and 0 का complement. So 1 का complement is 0. 0 का complement is 1. 0 and 1 is 0. 1, 1. Your function can contain both the ones. Okay. 1 का complement and 1 का complement. So 1 का complement is 0. 1 का complement is 0. 0 and 0 is 0. So you can have any number of Boolean functions. Fine. Okay. Now sometimes in exam you get how to prove. Yeah, prove. Fine. So at one side you are given x and another side you are given y. So what is your x? X is x1 and x2 or x1 and x3. And what is y? Y is x1 and x2 or x3 complement. Can you prove x and y are equal? Can you prove? Anyone? X and y?
Yes.
Yes.
Yes, sir.
How many variables are there?
3 variable.
We can also say 3 inputs.
Mhm.
Okay. Fine. Can you these inputs, all these 3 inputs, x1, x2, x3, they can take value 0 or 1. 0 or 1, 0 or 1. Fine. Can you prove x is equal to y? This is x and this is y. Can you prove x is equal to y? What you have to do? See, you please make truth table.
Yeah, this sir.
Yes, truth table will show you the result. Make truth table. First, take x1, x2, x3. As we are having 3 variables, so number of rows will be 2 की power 3, that is 8. Fine. So you have to draw like this: 0, 1, 0, 1, 0, 0, 1, 1, 8 rows. फाइन, 1 2 3 4 इस तरह से. Then find x1 and x2, x1 and x2. Then find x1 and x3, x1 and x3. Then find this complete. Yani ki you are having this, you are having this, and you have to perform ORing. Suppose this is A, this is B, you have to perform A or B. Yani ki A is your x1 and x2, B is your x1 and x3. Fine. So just fill it. If your this result comes out to be, here also you want to x1 x2 x3 and perform everything, at last you have to perform x1 and x2 or x3 ka bar. If these values come equal to these values, it means both are equal. Is it clear? So using truth table you can prove both the expressions are equal or not.
Yes, ma'am, we can.
Yes, you can. Na? So you easily form the table, but form table step by step. Like put 3 variables and then perform this, and at last perform complete. Here also perform x1, perform x2 or x3 ka bar, and then perform complete, final. Is it clear? Is
Yes,
it
ma'am.
clear?
Yes, ma'am.
Yes, ma'am.
Now can you create circuit for this expression? x1 का complement,
Yes.
x1, yes, x2 and x3 का complement. Or
Yes, ma'am, it is easy.
easy? Is it easy? x2 का complement or
Yes.
x1 and x3 complete. So how can you proceed? x1 का complement, see, fine, x1 का complement and x2, fine, x2 and x3 का complement. So x3, now we have to find x3 ka complement and is it clear? Now or for ORing you need x3. So take from here x3. Before doing the negation you have to take, because you have to take x3 only. So x3 and ending has to be performed with x1 or x2 ka bar. Fine. x2 ka bar, x2 का bar, fine, x2 का bar and x1. Whenever you are crossing the circuit, just put C type symbol. In this way you have to proceed. Fine. Now you can create. Suppose I have this variable x1 and I want to take x1 down. X1 is required in another gate also. So do this. Fine. And suppose you need x1 ka inverse. You are having x1, you need x1 ka inverse here in another gate. So what you will do? You will do x1 ka inverse and then you will provide x1 ka inverse or x negation to another gate. Is it clear? Fine.
Yes.
Okay. In Boolean expression, there are two types of forms: disjunctive normal form and conjunctive normal form. How will you identify disjunctive normal form? How? Disjunction. You know what is disjunction? Or. So, in any expression, if suppose these are sub expressions A, B, the joining element will be your disjunction. Then you will say that this normal form is disjunction. Disjunction normal form. In short, we write DNF. Disjunction means or. So you can easily see or, 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 or. Right? So you can identify disjunctive normal form. Is it clear? Then how will you identify for any Boolean expression what is your conjunctive normal form? In short, we write CNF. Conjunction. Conjunction means and. So and will be combining different sub expressions. And will be combining different sub expressions. Suppose we are having first sub expression, second, third, fourth, up to nth. And which symbol is combining? And. For example, this is expression A, this is expression B, and which symbol is combining them? And or conjunction. So you can easily identify the expression that this is in form of conjunctive normal form, CNF. Fine. In DNF, or will be combining. In CNF, you will see and. So A expression is there, and some B expression is there, and some C expression is there, and some D expression is there, and. Fine. How you can find disjunctive normal form? Disjunctive normal form. Simply, if you are having, suppose, 3 variables, fine, and the variables are P, Q, and R, 3 variables. Fine. How many rows will be there in the truth table? 8.
8.
And here we are not representing in form of 0 and 1, but for 1 we are representing true, and for 0 we are representing false. Fine. Fine. So it is like 1, true, false. Yani 1 means true means 1, false means 0. True means 1, false means 0. True 1, false 0. True 1, false 0. Fine. 1 1 0 0 1 1 0 0. Okay. 1 1 1 1 0 0 0 0. Fine. Now see, for disjunctive normal form, now see the number of truth values, yani ki number of 1 values in result. In result, we are having 1 in these rows. This is the row in which we are having result as 1. This is the row in which we are having result as 1. This is the row in which we are having result as 1. True means 1. Right? So how can you convert this into disjunctive normal form? Disjunction, yani ki or. Disjunction means or. And here we have 3 expressions. See, P, Q, and R. See, P's value is, for this row, P's value is 1. Q value is 1. And R value is 0. So P directly, Q directly, and R with negation. And see, P true value is 1. Q 1. And for R, we are having 0. So we have written here negation of R. So this is the first expression. Because this is disjunctive normal form, or. Now the second expression. Second expression is this. See in this row, 1 0 1. For 1 we have written P. For 0 we have written negation of Q, and for 1 we have written R. Then this is the second expression. Then for this third expression, see its row, 0 0 1 0 0 1. Yani ki P will be negation, Q will be negation, and R as it is. So P negation, Q negation, R as it is. This is the third. And joining element is what? Or. So this is disjunctive normal form, DNF. And these are known as min terms. Min terms means outputs with the true values, output with the one value. Fine. Is it clear? Now you can find disjunctive normal form, DNF. Is it clear or should I repeat?
Clear, ma'am.
Not clear.
Madam, it's
It's clear or should I repeat?
Clear, ma'am.
repeat,
Clear?
ma'am.
Okay. You can take,
Repeat, ma'am.
you can click it. You can click the diagram. Fine. I need WhatsApp number of any one of you so that I can share the PPT. Fine. I will share, but I need number of any student. Fine. You can send me. Okay. Then from here, we can start the dynamic programming. Dynamic programming. Actually, this book is book number 1, and this book is having 3 units. Fine. This book is having 3 units. 3 units. Fine. First was your proposition. Third one was your Boolean algebra. Logic gates. Okay. And second unit was your dynamic programming. Because in this book, first and third were directly connected. So we have completed first and third. And now we are starting the second chapter of this book, that is dynamic program. Is it clear, class?
Yes, ma'am.
Yes, ma'am.
It was having 3 units. We have completed proposition and Boolean algebra, and now we are going to the second unit, that is dynamic programming. Fine. Is it clear?
Yes.
Class, is it clear? Okay. Dynamic programming. Is my screen visible?
Yes, ma'am.
Okay. Fine.
Yes, ma'am.
Okay. Now tell me, do you know what is optimization? How we do optimization in our real lives? What do you mean by optimization? Suppose I have one box. In this box, if I can accommodate 10 toffees, fine. First case. Fine. I have another box, same size. I can accommodate 20 toffees. Okay. So where you can see optimization? First case or second case?
First.
Yes.
Second.
Second case. Space is same. Same space. But in same space, output is more. We are accommodating 20 toffees here. So we have optimized. Fine. It means for same resources, we are using it optimally. Optimally means we have optimized. Fine. Suppose two students are having cars, car 1 and car 2. Same type, same make and model, same company. Same make and model and same company with same specification. And these cars travel same route, same type of route, equal distance, 10 kilometer, 10 kilometer. Fine. Car 1 is driven by Ram and car 2 by Shyam. Fine, 10 kilometer. Now, suppose the cost of petrol for car 1 is coming out to be 550, and cost of petrol for car 2 is coming out to be 400. So where optimization has been done?
400.
400.
Cost too.
Fine. Yes, you have minimized the cost. Minimize the cost. It means driving and care of the car is done in such a manner that the same distance is being traveled by the minimal cost. Fine. So this is what optimization. Now optimization is clear.
Yes, 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 ma'am. It means that maximize positive outcomes and minimize
Yes.
negative.
Yes. Minimize negative and maximize
Posi-
positive.
Positive outcomes.
Fine. So this is optimization. Okay. So dynamic programming is based on optimization technique. Fine. Optimization problems are of two types. Two types. Minimum, yani ki minimize. We have to minimize. So we minimize the cost. We try to decrease the cost. For example, in case of car petrol, what is optimal solution? Where we try to minimize the cost. Suppose we have one company and we are producing one product, so we need more profit. We need more profit, so we have to maximize the profit. Is it clear? So we can say, for example, optimization example, maximize profit, maximize profit, or minimize cost, minimize cost. Is it clear? If we are having profit, we have to maximize it. If we are having cost of transportation or anything, we have to minimize it. Is it clear?
Yes, ma'am.
This is known as optimization. This is known as optimization. Is it clear?
Yes.
How dynamic programming problems make use of optimization? How? In dynamic programming, we divide a bigger problem. We divide a bigger problem into similar small problems. Into similar small problem. Suppose we have one big problem and we have divided it into 4 smaller problems. And then we have used these solutions for the bigger problem, for solving the bigger problem. So what we are doing? We are dividing the bigger problem into smaller problems, and whatever result we are having, we are storing these results in table. We are storing these results in table, and later on we are utilizing these results to solve our big problem. Is it clear?
Yes.
Class, is it clear? And this is known as memorization. Outputs of sub problem are stored in a table. We are using a table to store the output of the smaller problem to reduce the time complexity. It means in dynamic programming, what are we doing? We are breaking the big problem into smaller problems. Fine. Suppose we have one big problem, and we divide that problem into sub problems. And whatever result we are having, we are storing result in table. We are restoring result in table, and later on we are using these results to solve our bigger problem. Right?
Like
This
the
is
divide and conquer approach in
yes,
algorithm.
yes. And these problems may be overlapping in nature. For example, we have a big problem. Fine. And we have divided into sub problems. 4 sub problems. This is the output result of first sub problem, solution of second sub problem, solution of third sub problem, and solution of fourth sub problem. So here we are having table. In table, solution of problem 1, solution of problem 2, solution of problem 3, and solution of problem 4. We are storing solution of problems, sub problems, and we are later using it. This is known as principle of optimality. See how principle of optimality works. See how. Do you know about the graphs?
Yes, ma'am.
Do you know about graphs? Yes, you know.
Yes, ma'am.
Okay. Actually, this is a single node.
Hmm.
This is a tree. And every tree is a graph. This is a tree. Every tree is a
Graph.
graph.
Undirected graph.
Yes. And this is a graph. Because a graph is having a cycle. Graph may or may not have a cycle. So graph cannot be a tree. A graph which is having a cycle, in which cycle is complete, cannot be called as a tree. But every tree is a graph.
Graph,
So
yeah.
graphical problems are used for finding distance between the cities. The city X and city Y, and we want to find the distance between X and Y, or we want to find the shortest route from X to Y. We can use the graphs. Suppose we have to lay out a network for internet, and we have to completely cover a particular city. So in that case, we can form a network of nodes. These are network of nodes, and this is what, this is a graph. Fine, this is a graph. So we need to have a shortest path problem, and we are defining principle of optimality, what it states. Suppose we are having, this is a graph, this is a graph, 1, 2, 3, and 4. We are having 4 nodes. Fine. And we have to move from source to destination. Fine. Source is A and destination is B. And in between we have nodes x1, x2, xn. These are the nodes. Is it clear?
Yes, ma'am.
Suppose we have found the path, shortest path. We have find the shortest path from A to B. It is, suppose it is now clear to us. Fine. So if this is the shortest path from A to B, can you tell me what is the shortest path from x2 to x1, xn?
From
Obviously,
X to XN, sir.
obviously this one will be the shortest path from x2 to xn,
Then, yeah.
because we have already find the shortest path from A to B. So this will be x2 to xn. Suppose we want to find the shortest path from x1 to xn. So this will be the shortest path. Definitely this will be the shortest path.
Hmm.
If we want to find shortest path between x1 and x2, this will be the shortest path. So this is what principle of optimality. Shortest path problem satisfies the principle of optimality. It means if if we have find if we have find this path to be the shortest path between A and B, so we can say that this is the shortest path between x1 and x2. We can say this is the shortest path between x1 and xn. This is the shortest path between x2 and xn. This is the shortest path between x1 and xn. This is the shortest path between xn and B. This is the shortest path between A and x1. Is it clear?
Yes, ma'am.
Is it clear?
Yes.
Yes. Is it clear?
Yes, ma'am.
Yes, ma'am.
The unit teach you the method of proof. Da خو موږ نه ویلی کنه. دا skip که کنه ویلی مو.
دغه شی پاتې دی، دغه بیخي نه تشریح کړی تاسو.
چی شدی استاد رفت؟
نه شاید بیرته راشي استاد. هغه تر ټولو نه پکې مهم پوینټس د ماما دي ښه څنګه مونږ یو ایکسپریشن په لاس باندې هغه مونږ پروف کوو. هغه دې پرېښو دغه تېر کلاس کې زمونږ وایفای برق لاړه نو انا پاتې شمال کېدای شي درته ویلی.
تر ټولو سخت یونټ هماغه دی ما په نظر.
It seems our teacher disconnected from us.
کسی است سلام به همه. کسی است که یونیت های اول دور پیشات خوانده باشه؟
Class, at what time were we disconnected?
نه شفیق جان قصد کرد نمیخوام.
Yes, at what time were we disconnected?
Madam, it is about 1 or 2 minutes.
Okay,
not
so we
more, I
have
think.
we had started the principle of optimality.
It is anything.
We had started the principle of optimality.
Yes, ma'am.
Okay.
Yes, ma'am, we
I
can
was
start.
taking example of a graph. Fine. Let me share the slide. So is it visible? Class, is it visible?
No, ma'am. Yeah, it's visible.
See again. Is it visible now?
Visible.
Okay.
Yeah, visible.
Okay. So the principle of optimality. Any one of you who knows what I spoke or what I explained? I have taken the example of a graph. If I know the path from A to B and it is the shortest path, so we can say that any node in between that path, that is for example x1 to x2, this is going to be the shortest path. For x2 and x1, definitely this is going to be the shortest path. Fine. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am. Go ahead.
You got it? Fine.
Yes.
Suppose this is a graph. See here. This is a graph. Fine. Is my graph visible to all of you?
Yes, ma'am.
Yes, ma'am.
This is a
yes.
graph. Fine. P, Q, R, S, T, U, V. These are the nodes. P is the source. P is the source. P is the source and S is the destination. I have to find the shortest path between P and S. So there are many paths. One path
Yes.
is like this. Fine. Another path, it may be like this. Another path, it may be like this. Fine. Another path, it may be like this. So there can be many paths. Suppose I find out, and finally what I got that this path is the shortest path. Finally, after calculations, I find out that this path is the shortest path. That is path from that is path from P to V to T to S. Suppose I am saying this is the shortest path. Fine, class. What principle of optimality states that if we know the shortest path, that is P, V, T, S. Now suppose anyone asks me what is the shortest path from V to T. So what will be the shortest path from V to T? This one. If anybody asks what is the shortest path from P to T, this will be the shortest path. If anyone asks what will be the shortest path from V to S, this will be the shortest path, because we have already found the shortest path between P and S. Is it clear?
Yes, ma'am.
So principle of optimality works for shortest path problems. Is it clear?
Yeah.
Okay. Fine. Okay. Now we have longest path problem. Longest. Suppose I am having source as A, fine, and destination as D. Destination as D. Is it clear? Fine. So suppose I am having longest path as this from A to B, B to C, and C to D. This is my longest path. Fine. So from longest path is A to B, B to C, and C to D. Is it clear? Now
Yes.
let me give answer. Find the shortest path between B and C. Find longest path between B and C. So what will be the longest path?
To see.
B to C. No, this one will not be the longest path. Longest path will be from B to A, A to E, E to D, and this will be the longest path. So we can say the longest path problem does not satisfy the principle of optimality. Is it clear?
Yeah.
Yes.
See. First, see shortest path problem. Fine. This is the source. This is the destination. And this is a graph. Okay. We have done many calculations. These are nodes C and D. Okay, fine. Okay. Now we have to find the shortest path. Suppose this one is the shortest path from A to D. And the path is A to B and B to D. Is it clear? Is it clear to everyone?
Yes, ma'am.
Okay. Now we know shortest path from A to D. Just tell me what will be the shortest path from A to B? This one.
A to B, yeah.
Yes. Iska subset. What will the shortest path from B to D? Again, subset.
B to D. Yeah.
Yes, again, subset. So we can say the shortest path problem follows the principle of optimality. Now let us take longest path problem. Longest path problem. Suppose these are the nodes of the graph. Here we are having source and here we are having destination. We have to find the longest path between the source to destination, that is from X to Y. Suppose the longest path is this. Suppose. So the longest path is from X to P, P to Q, and Q to Y. Is it clear? This is the longest path. Now I want to find the longest path between P to Q. So will this be the longest path?
Yeah, P to X, X to...
Will this be the longest path? Tell me, between P and
No.
Q.
No, it
ma'am.
is the shortest path. It would.
Yes, it is the shortest path. Longest path will be like this.
Yeah, like this.
So we can say that longest path problem does not follow principle of optimality. Fine.
Yes, ma'am.
Shortest path mein, whatever we have find, every subset was the shortest path. But in longest path, no. longest path is this x, p, q, and y. But when we are finding distance between p and q, we can't say this is the longest one. So this is the difference between shortest path problem and longest path problem. So in shortest path problem, if we have solved one major problem, we can find solution of smaller problem. But in case of longest path problem, suppose we have find the longest path between x and y. This does not state that this is going to be the longest path between p and q. No, it may happen that longest path between p and q is this. So this is what longest path problem. Fine.
Excuse me, ma'am. If we
Yes.
have directed graph, in that time we can.
Yes, please repeat.
And if we have directed graph, in that we can shortest path and longest path.
Yes. The case will be different for the directed graph. Fine. We have to see the direction of the edges where arrow is pointing. Fine.
Yes, ma'am. Where we can use this two problem? It is same like in programming we are having this algorithm and some other algorithms.
You are having many problems. Graph-based problem, prim algorithm.
Yes, ma'am.
Stahl algorithm.
It is seems like that or it's different.
Dijkstra's algorithm. Fine. Bellman-Ford algorithm. There are many graph-based problems. Fine. These are the
cost should be based on the vertices cost.
Yes. Floyd-Warshall algorithm. So there are many graph-based algorithm, and you will be studying these in the next class. Fine. These are graph-based problems, and you will be studying these problems in our next class next week. Fine. Graph problems. Okay. Fine. Class.
Ma'am, we don't have these topics in our syllabus. I don't know where it is.
Yes, just repeat.
We don't have these things, these topics in our syllabus. You
You have.
proofs.
You have. I will show them. You have Floyd-Warshall, you have Bellman-Ford, you have Dijkstra's algorithm in your syllabus. In this unit which I am covering, see your block number 1, chapter 2. Fine.
It's proof here.
See your chapter of dynamic programming, block 1. In block 1, you are having three units. Unit 1 was your proposition. Unit 2 is your dynamic programming, and unit 3 was your Boolean algebra. We have already covered the proposition and Boolean
Ma'am,
algebra.
unit.
Yes.
Yeah, sorry.
In unit
Yes, ma'am.
2 of
the second unit is
in unit
methods.
2 of dynamic
Methods
programming,
of
you
proof
have
here is written.
yes, is in unit
Here
2
is-
of dynamic programming, you have graph problems. Fine. Is it clear? Now we are doing matrix multiplication. Do you know matrix?
A little bit, yes, ma'am.
Application of dynamic programming. Dynamic programming. Matrix multiplication. Do you know matrix? What is matrix? Have you studied array? Yes. 4, 3, 2, 1. Let me
Yes,
take
ma'am.
one example.
Yes, ma'am.
0,
Yes.
3, 1, 5. How many rows are there?
Here 2 rows.
2.
Yes, 2 rows. How many columns are there?
4 columns.
3.
4 columns. Yes.
So 2 by 4. 2
2 by
rows
4, yeah.
and 4 columns. Fine. Is it clear? So this is what? Matrix.
Yes, ma'am.
In general, we represent a matrix like this. Fine. We can represent matrix like this. Now, how we perform matrix multiplication? How many matrices we can multiply at a time? 2 matrices. Okay. Singular is matrix and plural is matrices. How many matrices we can use to apply multiplication? 2 matrices. 2. Like this. Fine. First matrix and second matrix. Is it clear? Is it clear?
Yes.
And what you will do if you have suppose 4 or 5 matrices? How will you multiply these? Suppose A, B, C, D, E. You have suppose 5 matrices. How will you multiply? You multiply
You should take
and yes, then the result will be suppose 1 matrix, then P and C. Then suppose result will be suppose L, then L and D. Then suppose result will be G, then G with E. Multiplication, 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 multiplication. It means at a time you need 2 matrices to multiply. Fine. And the resulting matrix you can multiply is the third one, then third and fourth, and so on. In this way you can multiply. What do you know about dimension? Dimension of matrix? Yes, class. Suppose 5, 4, 3, 2. What is the dimension of this matrix?
22.
Dimension, we have 2 dimension and 3 dimensions,
22.
like
Row
the
and
number
column.
of rows and number of columns.
Green
How
column,
many
yes,
rows?
ma'am.
2.
2.
How many columns?
2.
2.
2 cross 2.
2 cross 2. Yeah.
2 cross 2. Now suppose I have matrix A with dimension, fine, 3, 2, and I have matrix B with dimension 5, 6. Can I multiply this?
No, ma'am.
Can I multiply?
No, ma'am.
No.
Why? What's
Yes,
the reason? ma'am?
because this column of first matrix should be equal to row of another matrix. These two numbers should be same. Only in that case you are going to multiply the matrix, otherwise you are not able to multiply the matrix. Now let us see A, B, 5 cross 4, 4 cross 6. Now can you multiply the matrix?
Yes.
Yes. Because here the column of matrix A, number of columns of matrix A is equal to number of rows of matrix B, यानी कि first matrix, second matrix. Fine. Is it clear?
Yes,
Is
ma'am.
it clear?
Yes.
Done? So there are two operations. Suppose we are having matrix A and matrix B. So we can perform two types of multiplication. A cross B and B cross A. Fine. A cross B. Suppose A's dimensions are 4. Okay, 4 into 3 and B is 3 into 4. A is 4 into 3 and B is 3 into 4. See, these are equal. So you can multiply. Is it clear? You can multiply. And what will the resulting dimension of the matrix? 4 cross 4. You will obtain the matrix of 4 cross 4. Now what about B cross A? B is 3 is to 4. So B is 3 is to 4. And A is 4 cross 3. Is it clear? So in this way, what are the resulting dimension? 3 is to 3. Is it clear? Is it clear? Class? Is it clear?
Yes.
Okay.
Yes, ma'am.
Suppose you are having two matrices, 5 into 4, 4 into 6. Can you compute A cross B and B cross A? See, 5 A cross B. So 5, 4 and 4, 6. Yes. The resulting matrix will be having dimension 5 into 6. Now B cross A. B is your 4 into 6 and A is your 5 into 4. Can you multiply these?
No, ma'am.
No, ma'am.
No, ma'am.
No. As so the reverse is not always true. Fine. There is no commutative property. A cross B is not equal to B cross A. Okay. Even you can't multiply it because these are unequal. That is why you can't even multiply. So here A cross B is possible, but B cross A is not possible. So in case of matrix multiplication, you have to look at the dimension. Is it clear? Is it clear? Matrix
Yes, ma'am. Yes, ma'am.
multiplication is associative. Matrix multiplication is associative. Let us take 3 matrices A, B and C. In general, let us write the dimensions. Suppose A is having dimension m into n, B is having dimension n into p, and C is having dimension p into q. Is it clear? Then at one time we can find the product of A and B, multiplication, and then multiply the result with C. Or what we can do? We can do product of B and C and then A cross product of B and C. There are 2 possible ways to multiply these 3 matrices. Their dimension are m into n into p, and p into q. So either we can directly multiply A and B and then result with C, or B and C and result with A. Is it clear? Is it clear? Is it clear?
Yes, ma'am.
Now see the dimension.
Yes, ma'am.
And we can multiply A and B. What will be the dimension? Dimension of the resulting matrix when we will multiply A and B. A is m and B
M and B.
n into p. So the resulting matrix will be dimension. What will be the dimension? M into p. Now what is the dimension of C? P into Q. So what will be the dimension of final resultant matrix? It will be
M and Q.
Is
N
it
and
clear?
Q.
M and Q. Is it clear? Now see, let us move to right hand side. Dimension of A is m into n. Dimension of B is n into p. Dimension of C matrix is p into q. When we will multiply B and C, P and P, what we will get?
N and Q.
N into Q. Now when we will multiply this A with this resultant, and
M and Q.
so we can multiply M and Q. So this is associative matrix. Fine. Okay. Then matrix multiplication here is associative in case of 3 matrices with the dimension Mn, Np, and Pq. So A, B, C is equal to A, then B cross C. Is it clear? So matrix multiplication is associative. Can anyone give me answer why matrix multiplication is associative but not commutative? Why matrix, anyone can give me answer why matrix multiplication is associative but not commutative? Anyone can give me answer?
Because the reversing matrix is not always right.
Yes, reverse is not possible. A cross B can't be B cross A.
Yes,
because
ma'am.
because A cross B, suppose 2 is to 3, 2 and 3 dimension, and B is 3 into 5 dimension. Fine. So here 3 into 5 dimension and A is 2 into 3. See, 2 to 3, 3 common. We can multiply, but here 5, when we are reversing 5 cross A, 5, 2. They are not equal. We can't even multiply. Fine. But in case of associativity, what you doing, ordering is same. Ordering is same. You are all B and C ka product. Fine. So this is equal. But whereas in case of commutative, we are reversing the order of matrix. And even we have seen here that they are not applicable for multiplication also. So how can it can be commutative? Fine. So matrix multiplication is associative but not commutative. Is it clear? Class, is it clear?
Yes,
So we
ma'am.
can say ABC is equal to ABC, but AB, fine, fine. Is it clear?
Yes, ma'am.
So we are doing matrix multiplication and we want to optimize it. We want to optimize it. How we want to optimize it? How? Suppose we have matrices A, B, C, D, and E. So there are different possibilities. We can multiply them like A, B, C, D. We can do A, B, C, D. We can multiply like A, B, C, D, E, A, B, C, D, E, and so on, and so on. So we want to know which one is the best. Which one is the best? So any multiplication with lowest cost, any multiplication with lowest cost will be best. Yani ki it will be optimal. Fine. So we have to find, suppose we have matrices 3 into 4, 4 into 5, 5 into 2, 2 into 3, 3 into 4. We have, suppose, 5 matrices and we want to multiply it. But we want to find among all the possibilities which one is the optimal one. Fine. Is it clear? Now you know what is my question, class. Now you know my question.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
We have to multiply many matrices, 1, 2, 3, 4, 5. In which order we should multiply them? In which order? Ordering can be like this. It can be like this. It can be like this. It can be like this. And many other options are possible. So which one is the best? So this is the case of optimization, and we need to find out what will be the best way to multiply these matrices. This we need to find. It means what should be the parenthesis, where we have to place the parenthesis, like this, or A, B, C, D, or A, B, C, D, E, or A, B, C, D. Fine. Is it clear? So there are multiple options and we have to find which one is best. Which one is best? Or we can say which one is optimal. We have to find out. Is it clear? Is it clear? Is it
Yes, ma'am.
clear?
Yes,
So
ma'am.
we have to optimize.
Yes.
So we can write, we have to optimize. We have to optimize the computation. We have to optimize the computation of product A1, A2, A1, product of these matrices. these matrices. We have to optimize the computation of product of these matrices. And this is known as, problem is known as chained matrix multiplication. Chained matrix multiplication. And the problem is known as chained matrix multiplication. Why chained? Because we have a number of matrices A2, A3, A4, A5 and so on, and we have to multiply these matrices and we have to find out the optimal way. Is it clear? Is it clear?
Yes.
Yes, ma'am.
Make it very clear that they should be comfortable in multiplication. Like how we can say that A1 and A2 are comfortable in multiplication? Dimension of A1 is 3, 4
If they
and
have the same
dimension of A2 is 4 into 5. They should be comfortable in multiplication. It means criteria should be that number of column of first matrix should be equal to number of row of second matrix. Then only we can multiply. And we have to find the overall cost of multiplication. Overall cost of multiplication of matrix. And cost will differ. If I will go like this, A1, A2, A3, A4, then cost of matrix multiplication will differ. If I will do like this, then again the cost will differ. Then if I will do multiplication like this, then again cost will differ. And I want to find the minimum cost. Minimum cost. So in which order should I multiply the matrices? Is it clear?
Yes, ma'am.
So the question is, if the chain of matrices, if the chain means multiple matrices, if the chain of matrices is A1, A2, A3, A4, suppose we have 4 matrices, then we can fully parenthesize means we can keep the brackets. Parenthesize का मतलब होता है, parenthesize means bracket. In what order we have to keep the brackets? Parenthesize. Then we can fully parenthesize the product A1, A2, A3 and A4 in 5 distinct ways. 5 distinct ways. Can you write 5 distinct ways in which we can parenthesize this? Just try. We have matrix A1, A2, A3, A4. Can you find out 5 ways to parenthesize this chain of matrices? Just try. Parenthesize this chain of matrices. Can you find out? Just try. Add the parentheses.
Yes, ma'am.
First can be A1,
A1
then
into A3.
A3, A4. Fine. It can be like this. Second can be A1, A2, A3 together. Then A4. Third can be, we can multiply A1, A2 and the result with product of A3, A4. We can do this way also. 4, we can do A1, then product of A2, A3. Fine. Then A4. Or what we can do? We can do A1, A2, A3, then A4. So these are the possible combination. So what will be impact of? What will be the impact of these multiplications? Impact of these multiplications on cost. There will be different costs. Suppose here the cost will be X, multiplication cost. Here cost, suppose Y, cost is Z. Suppose cost is P. Suppose here cost is R. So which one is minimum? Which one is minimum? Which one is minimum? So we have to find minimum of X, Y, Z, P, R. If suppose Y is giving minimum, so we will say the result is this. Matrices should be bracket like this. Parenthesis should be in this fashion. If Y is the minimum. Is it clear?
Yes, ma'am.
So we have to find which type of bracket we have to follow to multiply the matrix so that our cost come out to be minimum. It means we are minimizing the cost. So our optimization problem is we have to minimize the cost of matrix multiplication. Is it clear?
Yes, ma'am.
Class, is it clear?
Yes, it is
Yes,
clear.
This is
ma'am.
the problem. So should I do it in this session or you would like to do it in another session? As per your... Yes.
It's okay, ma'am.
Technique session.
It's better finish
Yes.
today. It's
Okay.
better to finish
And
today.
this is known as... Yes, ठीक है. This is known as matrix chain multiplication. Next session, next week, we will start with matrix chain multiplication. Fine.
Ma'am, we don't have this
Okay.
syllabus
Okay.
in our.
Ma'am,
I
what do you?
will provide.
Yeah.
Just give me mobile number of any student. I will provide you. Fine.
Yeah, ma'am, would you please clear
Just share, madam, in
It's not
groups.
showing in our syllabus,
Madam,
ma'am,
just share in the group.
these things.
I will share syllabus with you. Fine.
We
In group share.
Okay, ma'am.
Any one of you, please send me your mobile number. I will share the syllabus. Fine.
Madam, share in the group. Please
Okay.
share the group.
But I'm not in your. I'm not in your group.
Okay.
Just see whether I'm in your group. Add me into your group, then I'll share. Fine.
Okay. ma'am.
Add me in your group, then I'll share. Fine.
Mom, what's the phone number that share in the group?
Okay. Okay. I'll share. Fine. I will share. So we are closing the
Ma'am,
session.
ma'am, can you hear? Yes, ma'am.
Yes.
Yeah,
Yes.
we have another question. It would be really nice if you share with us the previous question paper of this
Okay.
subject,
Okay,
because
fine.
so we could know how all the questions and would be in the
Fine.
exam.
Fine.
Yeah.
Fine. Okay.
Maybe
I'll share.
3 or 4 previous
Okay.
exam
Fine. I'll
questions.
share. Okay. Fine. Fine. I will
And
share.
another
Fine.
question, ma'am. Another question, ma'am. In first block, which units are really important that we should study because the syllabus are very much or quite a
Okay.
lot of. So, yeah, which unit do you think is really important to us in first
Because
block?
I think every unit is important because the question paper covers every unit of the syllabus. Every block is covered. Every block is covered.
So
Fine.
there would be no choice, no option for us to select
The
first or
options will be
second.
available within the unit, but every unit is covered. Every unit is covered. You don't leave any unit. Okay, we will cover every unit. Fine.
But it is, yeah, but it is very much, in very less time. It would be impossible to cover
But I will
this.
give
That's
you
why
maximum.
if you, yeah,
I will
if
give
you
you
share with
maximum
us the
examples.
important,
Fine. Yeah.
Okay.
I will give you maximum examples to solve. Fine. Fine.
okay.
Ma'am,
Ma'am,
if you share the number.
Yes. Okay. Fine. I'll share. I have your number. I will share. Fine. I will share the syllabus
Ma'am,
also.
I have messaged my WhatsApp number. You can share it there.
Madam Jagdamba sir is here, presented here. He can add you. Then you can share the group.
Okay, ma'am.
Fine, I'll
Yes. If anything is to be shared with the students, ma'am, you can give it to us, and then we'll be sharing it to the WhatsApp group of the learners.
So, students, I will be sharing the presentation with director sir, and he will share with you. Fine.
Okay.
That's
Yes, ma'am.
That's also perfect.
And one more thing that, ma'am, if you can help the learner in solving the assignments, it means in the future classes, if you take some example from the assignment question paper,
Fine, sir.
so it will be helping them in solving the assignments.
Fine, sir.
Yes.
So from where I can get that assignment question paper?
I'll be sending you the question
sir.
paper.
Fine, sir. I will help them
Yes.
in solving.
Yes.
Yeah.
Thank you, ma'am. Thank you very much.
Sir, we have a question from you as well, sir. We haven't received the videos of the lectures in our LMS.
Yes.
Yeah, and
Yeah,
also
we are
the
working on that.
assignment. Yeah.
Yes, we are working on that, and hopefully by within 2 days we'll be able to upload the previous videos. At least until by Tuesday we'll be done by that.
Yeah, because
So please wait for more days.
Sir, and syllabus are different. You uploaded in the LMH.
1 minute.
LMIS.
Yes.
Yes, sir.
What you are saying?
To this session it was a little bit different from our syllabus. Yeah, especially the
It was
last
not
one.
in our LMS, sir.
Okay.
Only the unit 3 was different.
Okay, but this today means what you are saying that this whatever ma'am has taught you, it is the part of discrete mathematics, isn't it?
No, it is not in our syllabus of in discrete mathematics.
The last
It was
unit.
presented.
The last
Actually,
unit.
sir,
The last.
they have not studied the syllabus well. They're unaware
No.
of what is covered in which unit. So,
Okay.
Ma'am, just to share the syllabus in the group, then
I
we'll
searched
discuss later.
I searched all syllabus, but these topics were not in our syllabus.
actually,
Matrix
this is
multiplication.
your block number 1, unit 1 and 3 that we have covered.
Yeah, ma'am, but
I
dynamic
think Midam is right.
programming is not.
Just share the group and we then see again.
Okay.
Block
It's
1,
better.
Yeah,
unit
okay,
1 is
okay. We'll see.
propositional logic. Unit 2 is about
Yeah.
dynamic programming, and unit 3 is about Boolean algebra. So we have covered 3 units from block number 1.
Yeah,
Ma'am,
they
the
are very
second
much
one
in your
is
syllabus.
method of proofs. Yeah,
And I am
I
following,
think just
yes,
change
chapter
or
by
change. It
chapter,
is
ignore
better to
syllabus.
Ma'am, in
present
unit 2 we
syllabus
have
again.
a method of proof.
yeah.
Yes.
We don't have
Yeah,
a
in
dynamic
second unit
programming.
we have methods of proof. Yeah, yes, ma'am. In second
Yes.
unit
It's different
of
from your
first
syllabus.
block.
Okay, let me see what is there in their LMS and whatever, because I have shared the syllabus with ma'am.
Yes, sir. I am
So
following unit wise unit, IGNU syllabus. Even I am giving example from IGNU book.
okay. I'll myself check with the LMS syllabus and the syllabus which I have shared with ma'am. If any difference is there, I will see.
Okay, sir.
Yes.
Yeah.
Okay, sir.
Yeah,
It's
Sir
different.
Jack
You
Dumbo,
check.
please
Email
add
or
Midam
Facebook,
to
they
the
can follow
group.
him.
Then she share the syllabus in the group and we will connect to her
Okay.
every time.
Yeah, I will do accordingly. Yeah, we'll do that. Pradeep, stop the recording now.
Thank you.
Okay, welcome.
Okay, you can stop. Okay, bye.
Okay, yeah, thank you. And thanks, ma'am, for sparing your valuable time for the students.
Thank you, sir.
Yes.
Thank you, sir.
So we are going to stop.
Thank you, ma'am.
Yeah.
Good. Have a great time ahead.